Hello, everyone. This is Todd Daniel, your instructor for QBA 237, Applied Business Statistics. And I want to start by congratulating you for making it to the end of the class. Or maybe I should say almost to the end of the class, because we still have 1 week left to go. And in week 16, we are going to wrap up the course, reviewing everything that we have learned so that you can get ready to take the final and prepare yourself for the next course, QBA 337, Applied Business Statistics. It has taken us an entire semester to get to this point, so now we're going to take a little time to review what we have learned thus far this semester. Let's begin our review talking about the big picture of why we do what we do with statistics. Now, we learned about populations and samples. Our population is the entire group to which a theory is applied. It is the entire group about which we want to know something. Now, when we examine the entire group, we call that a census. But most of the time, we don't have the time or the money or the inclination to measure the entire population. So we pull a subset of the population, which is called a sample. We do our research on the sample. And our goal in research is to take what we learn from the sample and then apply that back to the population. We do statistics when we measure things, when we create means and standard deviations. But those statistics are properly called statistics when they are applied to the sample. If we create a mean and a standard deviation for the population, we call that a parameter. And so in the field of statistics, we take the statistics that we learned from the sample and we use those statistics to estimate the population parameter. If the mean of our sample is 50, we would estimate that the mean of the population must also be 50. But what we will find is that our sample estimators are not always perfect. In fact, there is sometimes error built in. We call this sampling error. It's the difference between our sample statistic and the actual population parameter that it is estimating. Because we want to take what we know from the sample and apply it to the population, we want our sample to look like the population. That is called a representative sample. It is a sample that accurately reflects the characteristics of the population. If our sample is not representative, then no matter what we learned about the sample, we can't apply it back to the population from which that sample was drawn. Well, you know that the population is the entirety of the group that we want to know about, and the closer that the sample size is to the population size, obviously the more representative that sample is going to be. So one thing that we can do is increase the sample size. The larger our sample size, the better our sample statistics are going to estimate the population parameters. But surprisingly, we don't have to use massive sample sizes. Sometimes a sample as small as 30 could be enough to be representative, especially if that relatively small sample size of 30 has been randomly selected from the population. A random sample is one in which each element of the population has an equal chance of being included. Now, random sampling is the best way to get a representative sample, but random sampling does not guarantee that our sample will be representative. Well, let's look at some ways that we can do sampling. There's systematic sampling. That's where we select one of the first K elements. What I mean by that is, let's say you pick a number between 1 and 10, or we randomly select that number. It's 8. And then we select every 8th element thereafter. Systematic sampling. Convenience sampling is very popular. A lot of research gets done this way. It's where you collect the data from a conveniently available pool of respondents, the people who are most easy for you to get to, which may or may not be truly representative. Cluster sampling is where you as the researcher divide your population into multiple groups, which are called clusters, and then you randomly select the clusters to research. Stratified random sampling is where you as the researcher divide your population into multiple groups, which are called strata, and then you randomly select members from those various strata. So what's the difference between those two? Well, cluster sampling, think of school classrooms. We want to survey something about an elementary school, and there are 20 different classes. What we're going to do is randomly select 4 classrooms to study rather than selecting everyone or selecting randomly from everyone in the school. So our clusters are the classrooms, and we study everyone in each of the classrooms that were randomly selected. With stratified random sampling, we're creating strata. Think about voting demographics. We want to have males and females. We want to have the racial demographics. We want to have religious demographics. And so we figure out what are those demographics in the population, and then we select stratified random sampling so that we end up with a sample that has those same demographic characteristics. When we collect our data, we put those data together and we create a data set. So data are the facts and figures, the numbers that we collect and we analyze and we summarize so that we can present them or so that we can interpret them, perhaps by doing some kind of statistical testing. The parts of that data set include things like the elements. The elements are the subjects or the participants. The elements go into rows in our data set. Observations are values that are assigned to only one element. So as you look at each of the numbers or the collections of letters, those individual observations are attached to each element or subject or participant. Now the variables are observations that can take on different values. Notice that annual sales, each of the numbers is different. They vary from each other. So that column of data is a variable. Our variables we put into columns, and the elements or participants we put into rows. Having collected our data, we will do descriptive statistics. These are summaries of the data. We may summarize in tables, in graphs, or as numbers. And when we use numbers, we tend to look for central tendency and variability. Especially, or always we will do that, when we have scale level variables. Let's talk first about central tendency. The 3 main ways that we would measure central tendency are the mean, the median, and the mode. So the mean is the mathematical center of our data. We always use a mean with our scale level data that exist on a scale. These would be like interval and ratio level data. To calculate a mean, we add up all of the scores and we divide by the total number of scores, which is n. Now the median is the geographic center of the data. We can use the median with scale level data, particularly if those data are skewed. But the median is the measure of choice for ordinal level data. And then the mode is the most frequently occurring score. We use the mode with nominal level data. Let me tell you a few more things about the mean. The mean, the mathematical center, is the point at which half of the scores in the distribution are below the mean, which of course means that half of the scores in the distribution will be above the mean. It is a mathematical dividing point. And when we select a value at random, the expected value of that randomly selected variable is going to be the mean. Of course, it probably won't actually be the mean. There will be some sampling error, and then we can use the average amount of sampling error to calculate variability. So variability is another part of descriptive statistics. It's also called the spread or the dispersion or a measure of deviation. We've talked about the range, which is the simplest way to measure variability. It's just the high score minus the low score in our data set. Variance is the average deviation squared, and the standard deviation is the square root of the variance. It puts the numbers back into the same level of measurement as the mean. Now, if your standard deviation is 0, then you have a constant. The standard deviation would take on a value of 0 if every value in that variable was the same. The standard error of the mean is the standard deviation divided by the square root of n. Let's talk a little bit about outliers and what they can do to our data set. Outliers are the extreme values. These will naturally occur in the tails because they're far away from the mean, and they will affect our distribution in specific ways. For the measures of central tendency, outliers will pull our mean toward the outlier and skew the data set. They will affect the median just a little bit. If you have one outlier, your median might slip 1 point in the direction of the outlier, and it will have no effect. Outliers will have no effect on the mode. For your measures of variability, outliers will increase the variance and the standard deviation, but the range is most susceptible to outliers. One outlier can increase the range dramatically. However, the interquartile range, the range of the middle 50% of the scores, is not affected by outliers, and that would be our measure of choice when we have a skewed data set. Among the many types of distributions that we learned about were the binomial distribution. Now, this is the distribution when the expected value of the outcome is 0.5. Think about a coin flip. What is the probability of getting heads or of getting tails? The probability of each outcome is 0.5. That's a binomial distribution. We also learned about hypergeometric distributions. This is one where instead of the expected value always being the same, the probability of success for each subsequent trial changes from trial to trial. We also learned about the t-distribution. We choose to use a particular distribution based upon whether or not we know the standard deviation of the population. If the standard deviation of the population is known, which is pretty rare, we would use a z-distribution. But, as is the case most of the time, when the standard deviation of the population is unknown, we use the t-distribution. The t-distribution has a mean of 0. And as we increase the degrees of freedom, essentially as we increase the sample size, then our margin of error or our standard error will decrease, and the t-distribution approaches a normal distribution. For interval estimation of the population mean, we would use a t-distribution with n minus 1 degrees of freedom, where n is our sample size. Then we moved into hypothesis testing. So we use our sample to make inferences about our population. That's called a statistical inference. We take what we learn from the sample and apply it to the population. One common way of doing this is to establish a critical region, a region in which we have values that are unlikely to be obtained if our null hypothesis is true. These are values with a very low probability. The critical value is the cutoff score, the fence that establishes the boundary of the critical region. If we have a one-tailed hypothesis test, such as you see here, then the critical region is in only one tail of the sampling distribution. Alternatively, if we had a two-tailed test, we would have a critical region in both tails on each end of the sampling distribution. So when is a hypothesis test more likely to be significant? Well, there are three things that you could look for. First of all, the mean differences. If the difference between the means of two groups is very, very close together, it's hard to find a significant difference between them. But when those mean differences are large, when there's a large effect size, then it's going to be much more likely to find a statistically significant difference. Also, when the standard deviation, when the variance is small. With the same mean difference, a large standard deviation gives us a large amount of overlap. But when the standard deviation or variance is small, then the curves are distinct from each other. It's easy to tell which scores belong in each group. And also, sample size can affect the likelihood of finding statistically significant results. So when we have large mean differences and small variances and large sample sizes, we are very likely to find statistically significant differences between our means. There are three ways that we could tell whether or not a test is statistically significant. Now, one way is to look at the probability values. We've learned about p equals 0.05, using that as a cutoff score. So we can look at the probability value of a test, and if our p-value is less than 0.05, the test is statistically significant. We could also look at the test value itself and compare that to the critical region. If our test value, the t or the f or the chi-square, exceeds the cutoff score, if it is in the critical region, then our test is statistically significant. A third thing we can look for is the confidence interval. The null hypothesis hypothesizes that the difference between the means is 0. So if our confidence interval includes 0, it's not significant. But if the confidence interval does not include 0, then our test is statistically significant. Another way to think about that is both the high and low end of the confidence interval are positive. They're both on the same side of 0. Test is significant. Same is true if both the upper and lower confidence intervals are negative. It's only when one is positive and the other is negative that it crosses 0. When we do hypothesis testing, the null hypothesis is tentatively assumed to be true. We say if the null hypothesis is true, then what's the probability we would get the scores that we actually achieved on this test? And then we gather evidence. More evidence against the null hypothesis is indicated by smaller p-values of our test, such as p-values less than 0.05. Now, if those p-values are small, we reject the null hypothesis, and we would then conclude that the evidence supports the alternative hypothesis. Common p-values that we may use to determine whether a test is significant would be 0.1, 0.05, and 0.01. So if we reject a test at a 0.01 level, it will be rejected at 0.05 and 0.1. But if you were to reject a test at the 0.1 level, it may or may not be rejected at the 0.05 or 0.01 level. Of course, anytime that we make a decision about a hypothesis, we could be wrong. We could make an error. There are two types of errors that we are concerned with, type 1 and type 2. A type 1 error is where we have a true null hypothesis that is rejected. In other words, there really is no difference, but we say that there is. This is called a false positive, and it sounds a little bit like lying. And so it's looked upon fairly seriously in scientific communities. We shouldn't say that there is a difference when there is not. A type 2 error is where we have an alternative hypothesis that is true. There is a difference, but we miss it. The alternative is not accepted. This is called a false negative. It may be that our sample size was too small, the effect size that we were looking for was too small to be detected, but we've made a mistake in which we've missed an effect that was truly there. And then there's some other things that I wanted to remind you about, such as the observation that higher confidence levels provide wider confidence intervals. And when we do a null hypothesis for a proportion test, the hypothesized population proportion is called P sub 0. It's the null hypothesis. And the sample size that guarantees that all estimates of proportions will meet a margin of error requirement is computed using a planning value of P equal to 0.5. The box plot is a graphical representation that is equivalent to the numerical representation called a 5-number summary. So we have an application section on the final, one in which you are given a data set, asked to open it in JASP, and run a one-sample z-test. So let me walk through some things that you will want to know for doing this application. The data set is called ball bearings, and the setup is this. At a certain manufacturing plant, a machine produces ball bearings that should have a diameter of 0.5 millimeters. So every hour, a quality control manager randomly samples 30 ball bearings to test the process to measure whether or not the average diameter of those 30 ball bearings is 0.50. We will assume that the process is maintaining a desired standard deviation of 0.06 millimeters. I am going to walk you through the steps to do this test in JASP. But let me reinforce this idea that I am not showing you with the data that you will actually use. So I'm going to call my data set small bearings, and I've completely changed every number in the data set. I have 30 instead of 36 observations. This is not the data that you actually have to work with. These are data that I'm using as an illustration. So you can see that I have downloaded the small bearings CSV to my desktop, and I've just opened up JASP. So I'm going to begin by going to the main menu icon, Open, Computer, Desktop, and there's my smallbearings.csv. As you can see, this is not your data. These are data I'm using only for illustration. So now that they are open, what I would do is go to t-tests. So yes, we are doing a z-test, but we actually get to it through the t-test menu. One sample t-test. I'm going to move my data. Now in your case, they will be called diameter. That will go into the variables box. And we're going to select a z-test. So for the z-test, we need to specify the test value and the standard deviation. The test value that we're looking for, those ball bearings should be a 0.5, half of a millimeter, with a standard deviation of 0.06. We're going to deselect student, because that's the t-test, leaving us with just the z-test. Now under additional statistics, we're going to grab the location parameter, and we're going to get the confidence interval, 95% confidence interval. We'll go with that, and the descriptives. So now that I can see my output, I'm ready to interpret it. I'm going to open this up a little wider, and let's see what we have. What test did we use? Well, we chose a z-test, a one-sample z-test. Although it says t-test, this is actually a z-test, and we chose it because we actually knew the standard deviation of the value that we were using for comparison. We knew both the mean and standard deviation of the population, if you will. What are the null and alternative hypotheses? Well, the null hypothesis would be that our test value does not differ from 0.5 or half a millimeter. The alternative would be that our test value does differ from half a millimeter, either higher or lower, because deviations in either direction could be problematic. That makes this a two-tailed test. So what is our level of significance? Well, first of all, it is a two-tailed test, and our alpha level is one that we use commonly. It'll be a 0.05, meaning that our critical value by definition for a z-test is going to be a 1.96 in either the positive or negative direction. Well, we've calculated some statistics. Our z-value is a negative 14.9778. That means it's smaller. The probability is less than 0.001, so tiny probability. And my confidence intervals range from a negative 0.18 to a negative 0.14. Neither of them, or let's say collectively, they do not cross 0. 0 is not in between those two negative numbers. All of this says that this test is statistically significant. The descriptives, the n value is down here in descriptives. It's a 30. It will not be the value that you will see in your ball bearings data set. The mean is a 0.3359, standard deviation 0.0455, and the standard error of the mean is a 0.083. Finally, what is the mean difference? That is up in the first table again. The mean difference is a 0.1641, a negative value on that. So what do I determine? This test is statistically significant. These groups are different. And because the mean difference is negative, what I can determine is that these ball bearings are statistically significantly smaller than the mean that I was looking for. Is this process out of control? Yes, it is. We are producing statistically significantly smaller values. If the test was non-significant, then our sample does not deviate from our population value. That's actually a good thing in this case. We don't want our ball bearing sample to be different from spec, and in this case they are significantly smaller than they should be. And that is how I would think through these results and this application. And that is all we have for this week. My name is Todd Daniel. I've been your instructor for this course. Thank you very much, and I wish you the best in your education.